So this is 3.5a. And this section is called rational functions, which means pretty much we're going to be dealing with fractions. So we're going to be graphing and simplifying and all of that good stuff. So a rational function is a function f that is a quotient of two polynomials. That is, f of x is going to equal polynomial function 1 over polynomial function 2. Okay, and q of x cannot equal 0 because then that would make it undefined, wouldn't it? So if you look at the top of page 301, it gives you some rational function examples. Kind of crazy looking, but kind of gives you an idea of what they look like. So it's a good idea to kind of get an idea of what a 1 over x looks like, or what something as weird as the second one in the second row, the x squared plus 2x minus 3 over x squared minus x minus 2. You know, it's some pretty crazy looking functions there. They're going to be very, very difficult to create, so that's why we're going to stick to kind of making sure that they're a little bit simpler. So we're just going to start with example 1. In this section is called the domain of a rational function. So again, I'm assuming that that's all they want us to find here. In fact, that's what it says. Find the domain and graph f. Alright, well, you know that it's going to look very similar to the top left picture on page 301 because it's got 1 on the top and then a variable on the bottom. So we know that when the denominator, x minus 3, is 0, we have x equals 3. So the only input that results in a denominator of 0 is 3. So thus the domain can be any number except that 3. So what they did is they wrote x such that x is not equal to 3, if you want to write it in a set builder notation, or if you want to write it the other way, not including 3, not including 3 to positive infinity. Okay? And that's pretty much it for that one. Minus 3 right here says that our graph is translated 3 to the right, so it's going to look exactly like that top left one on top of page 301, only it's going to be moved over 3 units. So one of the things that I want to put on here for you, I'm going to put that graph on here for you. Okay, it's getting dark at my house, so this picture is a little bit dark. But one of the things I want you to notice, we shifted over 3. So notice what we've got here. We have this graph that comes this way and then goes down. And it gets closer and closer and closer to this 3. And over here it goes this way and goes up and gets closer and closer and closer to this 3. But it will never cross the 3. You will never quite touch the 3. It'll get closer and closer and closer, but it won't touch it because it can't, because that would make this function undefined. So, this will get, it's kind of hard to explain because we're getting into limit theory, some calculus kind of stuff, but it will continue to get closer and closer, but it's just like any number. You can take half of it, and then you can take half of that, and then half of that, and just keep taking half of numbers, and you'd think you'd get closer and closer to 0, and you do, but you never quite get to 0 because every number you can take half of it. And it gets closer to 0, but it never reaches 0. Half of some number is never 0. So it's the same way here. We'll never get to that 3. It's just kind of weird stuff. So example number 2, top of page 303, says determine the domain of each of the functions illustrated at the beginning of this section. Okay, so what they want you to do is they want you to look at all of those equations on the top of page 301, or all those functions, and be able to determine what the domain is. So I'm just going to have you look at the middle of page 303 and look at that. Now the domain of the first one we just did, but that was with x minus 3, but it's whatever basically makes the denominator 0. Okay, that makes it not a function. So the domain is anything that does not make the denominator 0. So the second one, 1 over x squared, same thing is true. 0 will make that undefined. Now when you look at the next one down, the third one down, you're just looking at the x squared plus x minus 2. You're not looking at the numerator at all. So we look at that denominator, we break it up into two functions, x plus 2 and x minus 1, and x cannot be negative 2, nor can it be positive 1. So those are the two numbers that it cannot be. Now the 2x plus 5 over 2x minus 6, you factor out the 2, you have 2 times the quantity x minus 3, and x again cannot be 3. The next one down, second to the last one, again we're just looking at the denominators, x squared minus x minus 2 breaks down to x plus 1 times x minus 2, so therefore x cannot be negative 1, nor can it be 2, but it can be everything else. And finally, the last one, negative x squared over x plus 1, x cannot be negative 1. Okay, not too terribly difficult there. It's just looking at the denominators and determining what x cannot be. All right, next section is called asymptotes. Now, an asymptote is basically that is a vertical line that shows where the graph can get close to, but will never cross. Let me take a picture here. All right, so there's a picture. Now, this is called the asymptote right here. This line here, because this is the one we just had a little bit ago. This means that it will never cross the 3, this vertical line through here. So that's called the vertical asymptote. All right, so x can approach 3, and as x approaches 3 from the left, it gets more and more negative. The y value gets more and more negative. As it approaches from the right, as it approaches 3 from the right, it gets closer and closer to 3, and the y value gets bigger and bigger. And notice, when we're talking about these graphs, we're always approaching the asymptote. So we're approaching it from the left, and we're approaching it from the right. So as we approach from the left, our y value decreases without bound, meaning it goes on forever and ever and ever. When we approach the asymptote from the right, it goes more and more positive without bound. Okay, so when they say without bound, that's what they're talking about. So there's a way that they write this. They will write, let me make this smaller here, I want to keep this here. Alright, they will write f of x approaches negative infinity as x approaches 3 minus. This means x approaches 3 from the negative direction. So this is this part of the graph. We're approaching 3 from the negative side, okay, from the left side. So you just assume on a number line, left of 0 is negative, right of 0 is positive. So from the left-hand side, we're approaching 3. That's what the negative is. So if you're approaching it from the right-hand side, it would be 3 plus. This just means what direction you're approaching the 3 from. The right direction or the left direction. So that's what that means. So let's look at these middle of page 304 drawings. So f of x approaches infinity as x approaches a from the left-hand side. So so a is right here. Okay, so this letter right here is a. So as this red line approaches a, as it comes this way, what happens? From the left, from the negative. As it approaches this, f of x, or y, gets closer and closer to infinity. As it goes this way, my y value goes up. So my f of x approaches infinity as x approaches a from the left. F of x approaches negative infinity as x approaches a from the left. F of x approaches positive infinity as x approaches a from the right. And f of x approaches negative infinity as x approaches a from the right. So it's going this way. Okay? So basically your vertical asymptote, your little dotted line that goes up and down that we've been looking at, are the zeros of Q. Okay? If we have a denominator, if we have 2x minus 11, and we have that over x squared plus 2x minus 8, alright, whatever makes our denominator 0 is our vertical asymptote. Okay, so that's all we're really going to focus on there. So what we're going to do is we're going to factor that denominator to an x plus 4 and an x minus 2, and therefore we have two vertical asymptotes, negative 4 and 2. What makes this 0? What makes this 0? So when we have the graph, right there, we have a vertical asymptote at negative 4 and 1 at 2. So whatever makes the denominator 0 is my vertical asymptote. And then when I graph this thing, I get a crazy graph that pretty much looks like I've got part of it in here, part of it out here, and part of it out here. We haven't learned how to graph those yet, but that's what it ends up looking like, because notice none of the graphs cross here, none of the graphs cross here. Okay? Now when we have the second part, the B part of example 3, we have g of x equals x minus 2 over x cubed minus 5x. Alright, so again, we're concerned about that. So we're going to factor out an x. Okay, so we get that. And so x can equal 0, or x squared minus 5 equals 0, or x squared equals 5. Square root of x squared gives me plus or minus the square root of 5. So therefore, I have 3 asymptotes, there and 2 there. So 0, I'm going to have that one. Square root of 5 is just a hair bigger than 2. So I've got one there. And I've got one there. And then when I graph this guy, let me get a better color here. I get a crazy graph that's looking like this. And you do not want to graph that, do you? Okay, finding the points to that would be a real pain, but that's what it looks like, and that's what happens when you have 3 different asymptotes here. You've got all these crazy graphs, but none of them cross the asymptote. Okay, I'm going to stop here and continue on with the second video.